So, with this, I would like to introduce Daniel, who will give us a talk about computers as a whole. He does holistic research on computers, so not just the hardware, but how it all comes together. Thank you and welcome. Thank you for giving me the stage. You might know me from previous years on the Rhein-Ruhr stage. Now we're here on Forschung. In preparation, or earlier, I talked about a lot of very specialized areas, and today I want to make it more holistic and talk about computers. And we'll go into different directions. So let me give you an overview. First, I would like to talk about what it's like to design a computer as a whole. So not just the thing that you're looking at in the shelf, but also what's within it. And the second part is what you can discover when you've bought a computer and how you. And third is what is between us and the computer. That means platforms and systems, as well as interfaces and layers. And at the end, I would like to invite you to go a step further yourself and introduce you to some research and some possibilities where you can become active yourself. So, design. Designing a computer is not something you do just like that. There's a lot of inventions that humans have achieved, and they all took time. And the term design is relatively new. In the 1960s, the term design was for the first time introduced into computing. And people began to define the term more sharply because design can have a lot of meanings. You can design clothes where you think of fancy clothing, but it has other aspects as well. Design has the purpose of helping to find solutions. On the other hand, design should deal with complexity. That means analyzing things, understanding things, and thinking about things differently, giving them new names maybe, or creating a better way of understanding them. So that makes it an iterative process. You go one step and then maybe you improve on that step, try out new things. I want to talk about computers today. And when I built my first computer in the 2000s, there were sharp edges in the computer. You could actually cut your finger, and of course that happened to me as well, because I slipped my finger somewhere. So at some point, people got the idea that maybe you should trim down the edges so you can't hurt yourself when building a computer. So people started to think about how can you design design. That sounds stupid, but design thinking is something like a framework. It goes from finding ideas together with a colleague, people getting into conversation, trying to define things, define what makes up a product, and then you develop prototypes, get feedback on them, And all of that is repeated several times or runs in parallel even. And the Interaction Design Foundation founded itself, and on their websites, which are linked, you can find a lot of literature. And they also have conferences on the topic. For example, I've linked you a paper, and I can recommend you to have a look at that because it helps you get a deeper understanding of the design process. Now I would like to come to the principles of good design, because that isn't easy. When you buy a product, you tend to think about, is that really a good design? Do I like it? And someone really thought deeply about that. That was this Dieter Ram, and he did that in the 1970s. He asked himself, is my design a good design, or what makes a good design? And he found 10 principles which are relatively well known. And I'd like to show you them. So good design first is innovative. So do you create something new? Are you creating something new, or are you just reheating something else? Is your product useful? Is it useful for its users, or is it something they'll throw away in a few weeks? Or maybe is it something in between? So I already talked about fancy clothing. There's people who say, oh, it's pretty, it's a nice design. But that's only one of the 10 aspects listed here. Next question is it understandable? You can design products that no one understands. And we'll talk about that. And still today, sometimes even I am working as a software engineer, and sometimes I find products too technical. For example, in the last company I worked, then it's also about honesty. You shouldn't hide things. And this is sometimes neglected a lot. We want that honesty, and I would like to see more of that honesty. Also, for example, being conscious of the environment is part of design, making your product sustainable. One very interesting aspect is, did I overdo it? Did I do too much? And this is the aspect of complexity, which I mentioned earlier. We want to have a holistic look. So whole is like the term we're talking about here. And basically the adjective whole was turned into another adjective, which is holistic. And if you think about, sometimes when you think about products, people ask, well, who did that? Who designed that shit? Maybe some feedback was missing, and there's ways to improve that design. There are things that are very difficult to design, for example, building a house or a hardware. In software, it's different. We'll get to that later. Then there's these typical questions. Why didn't they consider this? This is just so obvious. So, for example, sharp edges in a computer. Why didn't somebody think that people could hurt themselves? Why don't you round off the edges? Why didn't anyone think of this? Well, they learned from it. And this is the iterative part of the process. There'll always be a new design, a sharpened design. So we want to look at the system as a whole. When designing a computer, from the outside to the inside, make it transparent and understandable. And that isn't easy in itself. Like building a city or building a building, a lot of those same thoughts come in there. For example, the environmental or energy saving aspect. So in this image, this is about the whole. So you could apply that to a city or even a whole country. So how does the product, for example, affect the people that are using it? There are so many things that would be easy to fix. For example, like public bins or public toilets, if you think about cities. But on the other hand, someone has to be responsible. People also have to be responsible. For example, if a bin isn't available, they need to find another one. So if you want to make good design, you need a lot of knowledge and experience, especially when it comes to computers. Knowledge is also something that is very current in research. Knowledge is being researched on. You can classify knowledge as explicit and implicit knowledge. So explicit knowledge is something you can write down, and that we can basically give someone a book and say, hey, this is everything you need to know about X. Or you can have a series of lectures about it at uni or at school. This is direct transfer of knowledge. And what about things that you can't easily write down? This is what is called implicit knowledge. It is something you learn by doing, by experimenting. For example, it can start with children. When children start walking and speaking, when parents try to teach their children to speak, they, like when you think about how did I learn to speak, this is not something you would know consciously. It just happens. So a lot of things happen subconsciously. You pick it up along the way and you don't really question it afterwards. And there's a whole science that tries to look into those processes. And then we have subcategories of knowledge. There's a kind of knowledge that isn't just subconscious, that just comes from experience. This is tacit knowledge. It is something you gather, for example, while working a job. It's just those things you basically just know. It's things that are usually not written down, and where sometimes people are like, why did no one ever write this down? Let's write it down now. And it's not even easy to explain it. And the other thing is that takes us back to companies, for example, or even your own whole household. It's called tribal knowledge. So that's knowledge that only specific persons or groups of persons have. And it may even be things that we forget and that are never written down, but still people know it. They know how it works. And for example, a coffee maker. You've long since lost the manual, but you still know how to operate the thing. So this would be an example of tribal knowledge. Or sometimes there's a niche person who's responsible for a certain task. And if you think from the company's perspective, you would have to be careful because that person might not be there at some point. And this is also a thing that applies to computers. I would like to now give you some thesis. My first thesis would be that we have a lot of knowledge about computers, but it's very hard to transfer that knowledge. So, because when I start using a computer, I learn so much, not just general concept, but also very specific knowledge. People who are trying to get used to different operating systems often have difficulties. They have to transfer some of the knowledge they know from their previous operating system, but they kind of need to get to know the specifics of the new operating system.
And then it's still some sort of a mystery of what can I transfer from one computer or product to maybe another one. Maybe I have one laptop that has a control and key on the left side, and then there's the FN key that maybe enables different functions right next to it. But then there are computers that maybe have it the other way around. And I bet that there are many of you that have suddenly used a different laptop and are not used to that. And then there are people that actually will reconfigure their keyboard to have it match. And so maybe the question will occur, what can we do with this to make this more easily understandable? And so the question becomes, is my design a good design? Did I make this understandable? There are companies that actually decide to do things differently just to be different. There's one that might be more well known that creates a lot of devices. There are lots of functions that are very different. There are keys you might not find when you use them for the first time, or maybe they're not even labeled. And now, I will take a few steps back. How did we get to even having these computer things? That actually started a long time ago in the 1940s. There were the first electromechanical computers that were built. The Harvard Mark I, for example. Maybe you know the place Harvard. It was a so-called general purpose computer. You could actually use it for various purposes. And this term computer actually only created a bit later, over time. Before that, it was more of a calculator. And you will probably see this term with a different example later. And the people that worked on this, one of the first computers, were Richard Milton Block, Robert Campbell, and Grace Hopper. That's probably a name that many of you have already heard, and because they did very interesting things. And invested a lot into the development of computers and computer science and computer engineering. So they also had the idea of maybe creating a language for computers that is independent of the specific machine, and wanted to try this because they had this idea. This language she created was called Flowmatic. But it was the basis for COBOL, which many of you will probably heard. Even modern-day AWS, Amazon Web Services, allows running COBOL on their machines. That's a language that is almost 80 years old, and it can still be used. And this is what this looked like with the Harvard I. It used a system of punch cards, and this is a bit more difficult than what we do nowadays with just writing some text. It was harder to read and especially write. But okay, let's keep going for a bit. After a while, the electronic computers came up. An example for this is the ENIAC, which was also a general-purpose computer. It was the first one programmable digital computer. And here as well, there were a couple of people that programmed these first. This was usually women, by the way. There was Betty Hobberton and Marilyn Meltzer and Ruth Teitelbaum. They can actually be seen in this picture, replugging various cables to program. Francis Spence also worked with this machine. So what did they leave us? They actually invented the concept of breakpoints, which is something that is still used a lot in modern-day software engineering to stop a machine, to have a look at the current state of the system, what is currently going on. You have to think of this concept at some point. Kathleen Antonelli actually thought about these huge programs that they wrote and thought about whether one could group sections of that to run repeatedly. That's basically the concept of subroutines. This was very important because the machines were huge. Imagine it like a series of fridges. It's kind of similar to what you can see in a modern day computing center. This was just one computer back then, because these small integrated circuits were discrete wires. But then things got a lot easier. At some point, people got the idea, how can we create a switch, but digitally? Maybe that was not the actual thought, but it's basically what they did. So I'm showing a small schematic transistor here. It has 3 poles. There's an input on the top and an output on the bottom, and depending on what's given on the side, it might allow current to flow through or not. And we can even celebrate a small anniversary here, because on the 23rd of December, the transistor turned 75 this year. There were a couple of articles in various newspapers, which you can also find. So, this was the year of 1947, where the first transistor was built, and actually was produced a lot quite soon. I want to reference and lead you to the page pbs.org here. They have a large archive with a lot of knowledge about how the transistor was created and lots of interesting images. Alright, so programming languages, we already talked about Formatic, but there is a language that's a bit different, and that's the so-called assembly languages. So people that work with low-level programming, like microcontrollers and maybe other things, might have heard of this or maybe even use it. Assembly languages are also very, very old. They stem from 1947. This is Kathleen Booth that had the idea back then. This is also a somewhat more tragic anniversary. She turned 100 this year and then died. And she, together with her husband, designed computers, and these were some of the first programmable computers. And this was one of the largest breakthroughs that happened in this realm. And the idea of the assembly language was that users can actually read the machine code. This was a design. How if I want to use this language, I can't really talk a lot about Formatic or COBOL because I have never used those languages. But with assembly, I have worked a lot. And, well, if I know how this machine works on the inside, then I can actually use this assembly language a lot. It helps me a lot to understand what's happening. I'm writing to this register, I'm changing the state. And all of the higher level languages actually also mostly just refer to these things, these concepts. So this was one of the first programmable computers that had a storage, actually. And this was called the EDSAC, the Electronic Delay Storage Automatic Calculator, not computer. So where did this come from? This came from Cambridge, actually, and they actually wrote a very extensive manual for this design. They described how does this work from the inside, and included all of the details in their manual. This is not really understandable anymore nowadays. There was an assembly language for this, actually. It was called initial orders. That maybe sounds a little confusing, but it's also very interesting. And they had this diagram. That's what that looked like. There was a starting button, a starter button. That's what we know from nowadays as well. Then there's a starter. There's a storage, a store. Something to read things, something to record things. And the computer, written with an O. That's where you can see that this might be a little bit older and from Britain. And yeah, so the actual other way to write it came later. And then there was a company that figured they wanted something like this as well, and they were called J. Lyons. They actually operated tea houses and started making computers later, so-called geocomputers. And that's also what the company called it itself. And the Helio 1 was actually based on this concept.
Ende der 50er, 58, 59, da hatten Leute noch eine ganz andere Idee. Noise, also so wie nice.
And I'm 58. People changed a little bit. There's Robert Noyce started with Fairchild Semiconductor, and he started developing integrated circuits. And he was wondering, how was I working with the transistors? It's not possible to slim them down further, make them even smaller. And finally, we have the option of creating a very small one, and it pretty close to what we have nowadays. And they are just like fingertip-sized little circuits. Not sure if that's just a picture of an IC of its actual the real thing. But in parallel, and a little bit earlier, Jack Kilby had a similar idea, but it was not the exact same idea. The idea of Robert Noyce was more purposeful. We skip ahead another 10 years, and we come to the age of the home computers. You probably heard of them from old tales back in the days, and some people over years might be a little bit older, might remember. Among these, there were a few of these. That's the holy trinity of the home computers. At the end of the 70s, we have the company Commodore, Apple. There were a lot of computers that were started being manufactured compared to what we saw earlier. Right? Those were more designed for research, but this one was more widely spread. These you had like multiple. You could just go to a shop and buy them. And the earlier models we saw, they are often not. They don't exist anymore as a whole, and they ended up in museums and ended on displays. They consisted of a lot of parts. But there it continued to home computers. From the home computers, we continued to the personal computers. How is it to own your own device? That would be cool, right? The Kenback 1, that's considered the first personal computer. That's around 50 years ago, and there's a Wikipedia page that's dedicated to the history of personal computers. The next one is Xerox. that was in the United States, and they made a bit of research on what you could do with one of those computers. And Xerox had the first idea to build like graphical surfaces, graphical user interfaces. What I'm just doing with the mouse, that was developed, invented at that time. Even Ethernet was introduced by them. What we know nowadays for all local area networks. That was back in Park, in a research center in Palo Alto, where they all developed this. We go a little bit ahead. We have a paradigm shift. The computer is not something anymore that just a programmer uses. We get to a point where this is like a consumer product. Everything we have nowadays, like what we're watching now, the live stream, for instance, this is all happening on a computer. It could be like a smart screen, but it's irrelevant. In the end of the day, it is a computer. And back at that time, that was not the case. The users of a computer were also the same people who were programming the computer. That's still the case today for some, but the majority of people are users and not programmers. And back in the days, you still need people who monitored the computers, who had to kick it a bit to make sure it is running. They were operating the device. Now that we have an operating system, the device takes care of operating itself. The next revolutionary step were the microprocessors. What is a microprocessor? A microprocessor consists of a lot of parts on itself. First of all, it's like an integrated circuit, but there's not only a computing unit, there's also a storage unit in there. The first of that kind was the Intel 4004. That's also around 50 years ago. It was a 4-bit computer, not 64 like nowadays. It's not a typo. It was literally 4-bit. Over the time, it became more, obviously. In 10 years ahead, in 81, IBM developed the IBM PC, which is still considered as the reference device. It was based on an Intel processor, and at that stage they started with the secrecy on the development. Within IBM there were only like a handful of people who knew what's going on in the development side of things. The first laptop came around the same time. It was based on the Intel processor, the same Intel processor, and they put a lot of thought into the design of that, and they took another industrial designer on board, like Jack Hall, and they thought about the whole process as a luggage, as a briefcase, that they designed the whole product around it. This was a very interesting accessory that was developed there. At this stage, we are gonna make a little stop on a time travel, and we start discovering the computer, go back to nowadays. I want to take a look at how do you discover a computer today. What is a computer? I told you about integrated circuits and processors. You have storage, you have peripherals, and when you think about it a little bit further, it's everything what we have in the computer nowadays, like the laptop computer I have in front of me. I'm surrounded by cameras, and they all include a processor. They all include storage. That creates a basis for our live stream. And I have like even a little small monitor in front of me, and there's 3 more just for audio that I can see. Like I'm still audible, gives me feedback, and they are like just totally normal, and we don't perceive them actively anymore. And I want to go and take a few more examples of everyday electronics. Just go into supermarkets, shopping center, have parking lots, and the sensors they show you give you information about the capacity of the parking lot. So that means at one part there are sensors that register is there a car on that parking lot, and then you have like a counter that counts down like the availability of the spots. Is the spot free or not? And it just keeps counting, and you can distribute those parking lots, and you can distribute them across different spots. And there are even guiding systems. If there's a big system, these are like guiding systems. Same for elevators, escalators, automatic doors. They can be weird sometimes, but they stop working from time to time. But I was at the university at Ruhr, and the escalators there, only 5% of the time it was available. It had to carry a lot of load, but we don't think about those details anymore, about the controls of these devices. We're used to it. We just stand on it, it starts moving. That's what the electronics are there for. When we get inside the supermarket, and we can see price tags, and I only consciously perceive them this year. They have like little Eink Displays. They are not very power hungry, very efficient, just need a teeny tiny bit of electricity to add there, but they're hanging there and showing us the prices all day long. Maybe a can of peas has price euro, and we can change that. They are sometimes they can be as fancy that they are connected, interconnected, and they can remotely be programmed. You could use it like an adapter to change them, but nowadays they are even remotely connected. It's like, and if we continue there to the till, to the checkout, we have barcode scanners. Very early, we had to write down by hand, or we had typewriters to write down the prices, and you all remember the tills with the little crank on the side. But nowadays we can do the self-checkout. We can pay electronically. I don't even need cash anymore. Where I leave fingerprints, I can just leave electronic fingerprints there. Now we go down to the more horrible part. It's the laughing in the background. We're going down to the IoT lane, so we're thinking about fridges that are interconnected, washing machines that can tell you, "Hey, I'm done." With a coffee machine, I wouldn't need it myself, but some people think it's helpful that they are able to see on the phone the progress there. All the gadgets we see, and USB sticks actually are a small computer. And in the industry, we have appliances for almost everything. In medicine, in the medical sector, there's so many devices that are, if you get an X-ray, there is so many electronic devices involved. And I took a closer look at a few of those systems. If you're interested, you can look for other talks by myself on those topics. And more interesting development that I consider more useful is the smart home, smart building. So if we remove the smart gadgets, because there are a lot of lunatic devices in there, but there are some useful approaches where we can use smart devices to be helpful, to collect data in a way where we can guide the traffic, change how we design streets and roads, and how to measure the air quality. And yesterday I saw a small report on the Hamburg harbor. It's so the density of buildings is so high. You need sensors to understand the air quality in that area to avoid people getting sick, and that's something you want to avoid, right? Another example, I was traveling around and I saw street lanterns. Some of them were on, some of them were off. And they turned on. When I approached them, they turned on, and then I turned around and I understood the ones I passed, they turned off again. So that means somebody thought about how can you avoid wasting energy by just turning on the lanterns while actually somebody's walking by that area. And as we saw, like the environment is a big topic, but we also have the entertainment sector. For instance, Google Stadia, which I added RIP there because it's like off the market. Google created these gaming controllers. They even send it to people for free sometimes, and the idea was how can you play a game? Maybe you can just play the game in the cloud, and you just need a controller. And back in the days, I already assumed this is like a dead duck. But on the other hand, maybe it would have been helpful because it's more energy efficient, and you don't need to have like a computer in every household. You just like run that centrally. But difficult to achieve, and now, as you can see, we only have like 3 weeks left. January 18th, that's the end of life for Google Stadia. And as you can see, I took that controller apart, and a lot of people are asking the question, can you use it for something else? And actually, it's not designed to be used over Bluetooth or something else. So if you hack around, you can get access to a few bits and pieces. And if you want to know more, feel free to talk to me about the topic. And we have a hackerspace in Bochum where we designed something similar in the labor. And hey, I noticed some people have like cool badges for their events, and I saw some on a conference in Australia, the ADOS conference, almost 3 years ago, and they had a badge like this, only 2 simple displays on it and a little microcontroller. And I told myself, we can do that similar thing. How can we do it more haptic, and what kind of form factors do we want to have? And that's, with a team member, we prototyped a bit around, and that's the board that we created that way. And a few design thoughts we put in there are going down the direction of modularity. You can reuse the idea, for instance, the board, for instance, even if you have no idea of those boards itself.
And of course, you can program the whole thing. You can't see everything in this picture. You have two little LEDs, they're glowing arrows, and you can also connect to more monitors with a higher resolution, and below that you can see two buttons. You might know them from older machines. They're like half a centimeter in width, just some little buttons. And underneath you have placeholders for joysticks. So, like the controllers that you know from today's gaming systems. And you can just connect them there. And the module itself that's on it can also be replaced. You can just use another module. Today, there's a lot of chips that are designed in a way that this is possible. There's so-called systems on modules. That means you have manufacturing modules that you can see here, for example. This square here that's a little darker with the metal plate is actually just inserted onto that plate, and it has a lot of pins. That means that you could also use another chip and do the same thing. I found that interesting, and maybe I can do some more with that. So if you're interested in that, just drop me a line. It'd be really interesting to do something different there. I just have to say that Google is suspending this project. And yeah, there's the link to our badge. And there's still people who hack consoles. It's still a thing. We had presentations at the Congress, but also in the wider hacker movement, who just took apart some Sony controllers and got into more detail there. All right. And then there's people who still design computers themselves. And this is what I want to talk about now. And this is what I would like to see more of in the future, people getting into their computers themselves for several reasons. There's such a big industry behind computer manufacturing today. So they're not really approachable anymore. If you have problems with your computer, if you're looking for info, you basically have to go to the internet. You don't know if it's a software problem, if it's a hardware problem. There's so many aspects that could play into that, and it's very hard to get an understanding. And we have the possibility to get away from that, to get an understanding of our computers. And I'll come to that in more detail later. One solution is Anacro. That was an interesting idea that kind of fizzled out after some time. It was a computer based on microcontrollers, such as the one we just saw, or others that are available in the meantime. And then you have a protocol that allows devices to communicate with one another. Another interesting product is Kilion. It's also something like a PC, and the form factor is it's exactly the same that we had in the early 2000s was called HTX. It's the size of a platin, and it's a design that many people don't actively think about, but it's actually exchangeable. There's one design on that's built on Raspberry Pi Pico, and only recently, a few weeks ago, there was a small session on that with a former Commodore programmer and Jonathan Pellet, who started the Neutron project, and they've written a very expansive book where they basically go into detail on the whole design. Okay, more computers. What else do we have? We've got MOS, which is a very interesting project by Daniel Mangrum. He wanted to do something with a strong performance, but still understandable, completely understandable for users. So what does performance mean? Maybe you have to go beyond the microcontroller. So he started looking into chip design. Neutron is not doing that at the moment. It's just doing using the Pico to build something on that. And MOS went a step further and looked into how to build one's own chip. And then there's the build an 8-bit computer from scratch. That's also very interesting. And there's a similar thing with the 8286 system. That was a thing in the 80s, 90s. That's also very interesting. There's a big YouTube playlist on that. That's really worth watching. And it's also based on different parts. How about mobile devices? There's some very interesting projects there as well. I just picked two. One of them is MNT Reform Laptop. The idea is to have a more personalized computer. Everything's documented. You can look at all of the different switches and different modules. It's basically a modular computer with a different form factor, but it's designed in a way that you can look into all of the inner goings on. Then we have a phone project. That's the Pine phone. You can buy that as a phone. And I have to be honest, the chips that this is built on are not that open. You can look at the code in big parts, but the chips aren't completely publicly documented. So if you look at radio technology today, there's a lot of secretivity. It has different motivations, which I won't explore on here. There's also bigger computer projects. A few of you might have heard of this one. There were people from Google and Facebook who have big data centers, and they have specific requirements. So they founded a community where they thought about how to design a hardware for those specific requirements. Because if you run a data center, you have to think about, say, you can only save 10% of energy. That's a huge factor, not only for the environment, but also economically. So for those companies, that's a huge motivating factor. And there's a few designs that you can have a look at from them. It's not all open, but at least you can look at a large part. Then there's Oxide. Oxide built a rack server, but they rethought the design from the beginning, because today usually you have many manufacturers involved in building those designs, and the software comes from a completely different manufacturer than the design of the hardware and the server rack. And what they want to do is supply hardware from very small companies, even in big data centers. So they might be a bit slower, or they might have this or the other bug, so that you have to get creative. And a few students had a similar idea. How can you downscale a rack? Because there's so many small computers available today. This is the Racklet project. That's very interesting. So I invite you to have a look. There's also an online meeting where I also take part regularly, and on racklet.io you can find the documentation. So single board computers, I want to have a look at that, because it's a very common architecture, but there are some aspects that you should pay attention to. There's a lot of single board computers which are marketed as open source. But you have to look behind that. What does it mean? For example, there's the Open Source Hardware Association who put some thought into that and who try to find a definition of open source hardware. So it means that you need to have the plans for the computers. So which components are used and how do they play together? The whole design of the board is part of it. Manuals and everything, how to work with those devices from the beginning, and an open license. Those are the minimum criteria. I'll add the source code. So, the source code from the beginning, from the start of the device and before that, should be open. There's so many companies who don't have open firmware. For example, Raspberry Pi. I went and asked them about what about open source code, and their response was basically, yeah, no. So I don't want to play the blame game here, because of course they have special contracts from where they source their chips and so on, but still, as the end user, I don't have a complete understanding of the whole product, and this is not what open source should be. I can look at the parts but not understand the system as a whole, and this is where I want to go. There's people from the community who are working on Linux kernels. Sometimes you can find zip files, so-called source dumps, so you can't even have a look at what is different now. So that's not cool. So if you want to build code, please use a tool chain that is actually that I can source from somewhere and that I don't have to scramble together from elsewhere. So tool chains that are ready to use, and even better, if you have to use your own, provide the source code. So, and if you meet those requirements, you can get a certificate with the logo which you see above. So you can file a request with the open source hardware and say, okay, I would like to have my product certified as open source by you, and then you have to jump through certain hoops. So it's the same like if for cars, basically, I can't just build my own car. I have to get it certified and approved. I want to talk about firmware. I already mentioned it a few times, but I would like to go into more detail. The term firmware is actually badly defined, or isn't defined at all, actually. Sometimes it's called the BIOS. And then you give people a Raspberry Pi, and there's a conceptual difference, and some people don't even know that it has and runs a firmware. So there's many meanings of firmware. People, for example, when they talk about firmware, they actually mean operating system. Sometimes the term firmware is stretched and includes like the user interface even. It depends on the manufacturer and the terminology they're using. Sometimes the definition is overextended, and sometimes it's the opposite. But the fixed part that is not really exchangeable, there are certain things that I need for my computer to become a computer. It's an interesting thought to think about, what do I even need to start a computer? Yeah, that's another thing. We're not 100% there, but that's okay. I think there should be an awareness for how it all comes together. And for people to be able to come together and exchange. For people to come into contact with small companies, for example, there's now a group, the Open Source Firmware Foundation, that came together as an umbrella organization, and they're saying that they represent our parties interested in open source firmware.
Okay, and another project that I want to include in the foundation there is my firmware editor. This is something with which I can load some firmware, maybe from a laptop or some other device. And this will then work by analyzing the firmware first, then it's visualized. For example, what does the storage use look like of this firmware? File systems are discovered, and maybe UEFIs, for example, is something that people might have heard. Then might be a bit of a different thing, but yeah, there's always a file system there. And there are some other file systems that may be understood as well, that are worth looking at. You can maybe wipe some files that you don't need. For example, if I have an email client on the firmware by default, then I can remove it there. Yes, I have actually seen that before. And I can also export some metadata from this, which is actually something you can give to other people and show them the interesting things that you discovered. An interesting new topic that is being added there within the understanding of computers that is commonly not talked about much and not documented very well is the idea of an SBOM, a software bill of materials. The idea is what things belong to the software. So you want to know where does the software come from, who wrote it, what components are inside of there, for example, that email client, and so on. Yeah, and now I started a new project that I want to go more into depth for this talk. So, what is... Well, okay, I talked about firmware, and firmware needs to do something before it can start an operating system. But what does that actually mean? So, we're talking about platforms and systems here. Systems, like operating systems, for example. Okay, so what's a platform? We can have a look at Wikipedia, and there's a quite large definition here, which says that it's a compute platform that is an environment where software is executed. Okay, I think that's a fairly intuitive definition. It's something that I can run and run software in. But then it maybe gets a bit more confusing. It can be hardware, or it can be an operating system, or it can be a web browser, or it can maybe also be programming interfaces, maybe some other software that's underlying. The only condition is that it can execute my program code. Okay, this can be lots of things now. Yeah, well, so what can also be included? There are various abstraction levels, maybe. Also, the computer architecture may be a part of that. Maybe an operating system, or maybe a runtime. Libraries. That's still similar to the sentence before. And then we have a bit of a more compact sentence. It's the thing that computer programs are run on. I don't really want to go into this definition for too long. But so yeah, there is a definition, but it's difficult to grasp it entirely. That is why I started this project. Platform System Interface is what I'm calling it. I want to have a look at these interfaces for what is a platform, what is a system, and I want to narrow this down and maybe be able to create some design guidelines from that. The idea is to create a specification, which is this PSI spec GitHub repository on the GitHub org, and the idea is to maybe find some different firmware projects and look at how their boot flows look, how they interact with the operating system. And how would I do that? Well, I have to look at all of the features that exist. I want to extract them, I want to compare them, and maybe evaluate and maybe even improve them. Maybe we can find some more useful designs. There's a small other thing that we need to explain as well, which is a small aside here. We will talk about buses now. This is something that is very important to a computer as a system. Buses, there are some very common ones. What's a bus in computing, for example? These are usually lines, data lines running over some sort of PCB. They can also be exposed, and a good example is the I2C bus. It's present in very many places, for example within your HDMI plug or even VGA, and that's how the computer even knows what resolution the monitor or the other side of the cable has. Often sensors are connected using this, for example temperature sensors. On Linux there's a tool called I2C tools, which can show what I2C devices are on this computer. Then there are protocols, which is the sort of the second half. To communicate with other devices I need some sort of protocol. And this protocol defines commands, for example, or information codecs. And as an example, a thing that one can look at is the SPI flash, which is a small storage chip that can be used in computers. And it can be read with a very small command. And in Orboot, which is a project that I'm currently building, there's a very small system defined how to read data from the storage. There's only a read command defined because we don't really need a write command at all. And then there's conventions and standards. If you think about how many things are connected via USB these days, for example, mice, keyboards, USB sticks, phones, all of these things can be connected to computers, but all of these will only work because we have this predefined interface. And this is something that that's how we create compatibility. And we create a market, because devices can market that they are compatible with USB. If you connect it to a USB port, it will work. But these buses are not only external, they are also internal buses, and they are deeply inside the computer. If you look at a microprocessor, it might often look like this. This is a basic schematic of a microprocessor, the small chip with lots of little legs. This is how this would look schematically from the inside. There is often a system bus, or maybe multiple, and there are lots of components that are inside of the chip package that will make out the chip in the end. There's a CPU for this, there's a little bit of memory. Then microcontrollers often have a ROM, a fixed non-volatile storage. And then there are lots of the rudimentary commands are embedded into this. And then there are interfaces, especially for things like systems on a chip. As an example, I included a UART interface here. This is a very simple part that I can use to connect something to exchange text. It's just a serial interface. And these individual components inside of this are also called blocks or cores. And if somebody talks about, hey, I have this 8 core, then that means there are 8 of these CPU cores, blocks, inside of the system, and that can communicate with all of the other devices. Another example is the so-called advanced high-performance bus, which is kind of originated in the ARM area, and it's the standard bus. For some reason, with ARM, everything is advanced. ARM means advanced risk machines, but the architecture is actually publicly available and well documented. Alright, so let's talk a bit about complexity, because I tried to explain all of this very simply. And so we have these different ideas of instruction sets. There's x86, which Intel and AMD use, which are very, very complex instruction sets. There are, I don't know how many thousands of instructions, and barely anyone can actually understand all of them, and that's why we have to document everything so people can actually use it and write software for it. And then there's ARM, which is still quite complex. The letters, the acronym is for R, the RISC is Reduced Instruction Set, but these are still hundreds of instructions that can be computed by this. And then there's a new idea here, which is called RISC-V, which is about 10 years old, and you can already buy chips for it. And their idea is that they created a modular approach for an instruction set for a computer. And they do that using open specifications. And you can basically, well, sort of easily, design CPUs with this. It's a bit simpler than ARM. but it's still reduced. So we're still looking from the perspective of a complex thing onto a bit less complex thing. We're still only at a bit easier. And that's why we want to try to reduce this even further. Neil Ford wrote a nice book called The Productive Programmer, and they thought that programmers are like complexity, like moths like light. There's yeah, and it's equivalent because it's a dangerous thing, and it can create more problems. Complexity can also be inherent or given, for example, just like in physics. But we are discovering physics. It's not something we're inventing. We just discover it the way it is. Maybe we're looking at it in different ways, but essentially that's just how it is, and we have to accept this complexity. And once it gets too much, we have to start reducing. And the opposite that we want to reach is simplicity. In software architecture, there are various approaches to achieve this. What is software architecture? Kevlin Henney, who recently gave a talk about this, is the thing where developers live. You can imagine this like houses, for example. They're something to live in, and people care about the architecture of those things, so they don't just fall into rubble, and has doors and windows. And that it's a similar thing with software architecture. Neil Ford said, yeah, most architects and developers pursue the latest and greatest and with great fervor. Yet the history of engineering, including software projects, contains, and that's why I mentioned all of these things, how all of this was created, yeah, includes lots of things that we can learn from, and maybe try not to repeat their errors. And there's this classic quote that says that those who don't know history are doomed to repeat it. So let's talk a bit more about firmware. There's something called UEFI. What does that even mean? It means something extensible. It's an extensible firmware interface. And this extensible is sort of a problem. It's marketed as something that gives you more functionality and more security. And now if you think about that, wait, more functionality, why is that more secure? Well, of course it's not. That's not really how it works. The more complexity we have, the more potential there is for errors. And so that's it's supposed to run with this evolution of devices. And a couple of years ago, maybe 20 years or something, people thought about how this may be able to be changed. And then there are people from Google and Facebook and Horizon Computing and Two Sigma, and they thought, how can we create something from this UEFI stuff and reduce it into something more simple, something that we understand better for our firmware. For example, let's include a Linux kernel. And that's how the Linux boot project was created. It was originally called NERV, the non-extensible reduced firmware. That's where we have this reduction aspect. And Microsoft had the same idea. Well, something is not quite running right here, and this is a bit complex, and they worked together with lots of hardware developers and firmware developers and wanted to reduce all of these interoperability problems, and they created this FASR project, the Firmware Attack Surface Reduction project, which is a way to also reduce the surface. So yeah, the security part of UEFI apparently didn't work quite well, because there's a large aspect of security problems.
And now at the end, I would like to start talking about layers and interfaces and maybe get a little bit of hint what you can do yourselves nowadays. So with layers, we have a small problem. It is an inherent problem. Here's a classic picture, XKTZ comic, that everything that we have that's in modern infrastructure, it's based on a very sensible component that can easily break. Not cool. What I would add here, if we are building layers, we will always have interfaces, and it is difficult to design an interface. And the more I have, the more problems I'm creating, and sometimes they are not necessary. But they also create creativity and spark creativity in that area. For instance, Linux BIOS. It's in 1999. In some data center, some computers were not working, and somebody realized that we can just add Linux here, similar to what we saw with the Linux boot, which then evolved into Coreboot. Say again, Linux boot. We just remove a lot of the manufacturer's parts and we just replace it by Linux because we can understand it better. And the question is do you own your computer if you don't own the firmware, if you can't understand the firmware? A lot of people don't care because they don't need that. They just understand it. But there are enough people who actually run into problems because of that. If you look around in forums, you find a lot of questions on where people raise questions like, can I boot from a USB stick? And further, these are all related to firmware problems. And we don't do. We just create a Pico host bootloader, and it's just loads. There's no huge user interface. Just load it. Similar approach you have in the open system firmware, which comes from the Open Compute project. They just specify how the firmware should be when you're creating the firmware, how it should be designed, how you should create the operating system on it, and the open system firmware group ecosystem. They can assist you there, and it's highly recommended to take a look there if you're interested in that topic. On the other side, you have the layering grows vertically. It will not get more pretty because of that. But you can also have components on the same layer. And I can also take a different approach where I offer various layers. I can offer different approaches. But if you don't have the ownership of these components, then you can end up being stuck with these layers. One approach is the approach by Intel. We make a 3-layer model for firmware. It's like the first level is done by us, that's Intel, and that is interfacing with the hardware directly. And above that, you have the layers. That's the SFSP components. It's a large collection of binaries, so they are not open. It's hard to really research them. You could find problems in there, but not easily. And nowadays, heavy load. They have multiple kilobytes just to initiate the RAM. That's something that there's potential to slim that down. In the open source firmware foundation, there is a group that's called Silicon Interface Design. They believe in the binaries that should work with a few components that is then made available to the open source community from a chip manufacturer's perspective. But from my perspective as a user, I have a different approach. And there you have me personally. I'm involved in the Rboot project. That's a firmware that's written in Rust, and I just want to quickly elaborate how our boot flow looks. It only has two parts, if at all. The first part is we just have a small boot part, and then we hand it over straight to the next part. There's like small things you can extend. You put in a Linux kernel, and that's the idea. The next part I have to shorten a little bit. It's runtime services. The idea is to abstract a platform. You define interfaces again, and you turn the software as part into part of the platform, which is problematic if you turn the software as part of the hardware layer, because that creates a new attack surface. And there's this company that creates research these vulnerabilities. And you have those variable runtime services that are platform specific. And you have, for instance, the SPI specific, and I'm going to have a talk in the next days about that. And that's where we talk about how to create those interfaces. But you always need to implement them on a per platform basis. They are not very portable, and that's why they have a group that has built around that in order to standardize these services. I'm afraid I have to skip a few bits and pieces. That's how calls look in those runtimes. I will give you more information about that on the talk the day after tomorrow. If we go from register to memory, we attract problems that we already solved. We're taking these back. The best idea is to just remove these out of the idea. What else can we do? That's how I come into my end on research and development side. Okay. How can we avoid in the project for some time you can find approaches how you can avoid forgeability. Else, what can you do in defending software, and what needs to go into the hardware? There's also something very new. It's a Cogent project, looks after this, and I only discovered it yesterday, but I can only recommend to take a look there. Hardware has also other vulnerabilities like Meltdown and Spectre. they were targeting at the micro-architectural designs, and you would need to redesign the entire hardware around it. Then you have trusted execution environments, where you have like a secure environment where you execute code. Another approach is confidential computing, where others can't see what kind of service are using that computing power. For instance, when you're like in a cloud computing environment where you want to avoid other people to see that execution. Some talks I can only recommend, and literature, very interesting. I will not go down into detail on all of these. The Patterson and Hennessy is the hardware and software interfaces are explained in the book by Hennessy. Another, create your own computers. You can get FPGA boards. There are frameworks. There are associations. For instance, the FOSSI Foundation, the Zero ASIC. There are also courses where you can learn to create that, and even Google offers you to help you creating your fabs. And now the final question: will your design be a good design? Thank you very much. Now, questions. The internet was very busy listening to your talk, and they have a lot of questions. Are there open source hardwares they are running on Linux cores? That's a difficult question, because I will have a talk in the day after tomorrow. We have a community that looks into the insights, and I have two platforms where we implemented all boots, where we manage the memory ourselves. We have a better understanding, but not a full understanding yet. For some parts, the community has a very, very good understanding. That's what I'm going to talk to tomorrow. The other is not as well documented, and the JH that's a little testboard by Eagle Foundation, where and we have the Vision 5 board with a follow-up product that are very similar, and they are in the orphan Obut source. In the linked Twitch stream, you can hear me talking about what single board is the most open source computer. If you want a closed source, get a Raspberry Pi, and if you want something open source, it's the Eagle board, and systems based on the All board and Rockwin. The All-Winner has been looked at a lot by other teams. There's a large wiki where I wrote a lot of articles on, where we have a list of a lot of different variety of boards, and I'm going to pick this topic up tomorrow again. And another question.
Wie spielt das Überspielen und Patches der Intel-Management Engine damit rein? Könnte man nicht analog Closed-Source-Chips Open Source kontrollieren?
Okay, die Frage ist, ich bin auch nicht 100% sicher, ob ich die Richtung der Frage.
I'm not sure if I understood the direction of the question. Rolling out patches for firmware. Only Intel provides these patches there are from updates from time to time. They come through the OEM manufacturer itself. They include that as part of their updates. And can you repeat the second part of the question? Could you not control closed source processors on an open source way? And yes, of course you could do that, but it's not if you figure out how that works. But it's not that easy. And it's potential. It's possible, but so far nobody has figured it out. Potentially would run into issues with signatures, and you will not access this. You will not have these keys, but you may find it somewhere.
Es wird gesagt, dass ja nur die nordamerikanische, europäische Geschichte betrachtet wird. Gab es auch eine Alternativgeschichte so östlich?
The question is there a different? This was a very North American European perspective. Were there also more Eastern perspectives on this? And yes, other companies more in Asia, like Panasonic, Japan was advanced. If you take a look at the Wikipedia page of the first home computers, where I looked at the Trinity, and there you will also find a Japanese version of the Trinity, and the former Soviet countries. And for countries context, we have to understand the countries were set up, unfortunately, very similar to today. They were not the best friends, and the Soviet, they created also their own varieties. But I just saw somebody on a vintage computer festival who was able to install Linux on one of the Soviet computer variants. So it's possible. That's how we close the